Hi guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, IIT-Jam exam, Tifr, Jest, and other exams related to physical science. So guys, this is the lecture number 11 of quantum mechanics, in which we are going to study step potential. Okay. So before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live classes, which are going to help you to crack the exams related to physical science. Okay. So we are going to study step potential. Okay, let me just check, am I audible or not? Subscribe my channel. Yeah, I'm audible. Okay, so I'm going to start now. So step potential. Step potential. Okay, I'll define step potential. So step potential is Vx equal to 0 when x is less than 0. Okay, if x is less than 0, then Vx is 0. Okay, and Vx equal to V naught when x is greater than equal to 0. Okay, x is greater than equal to 0. Okay, so this is the step potential. This is like this. Okay, so okay, I'll draw the line. Okay, I'm drawing the figure. Okay. Okay, so this is 0. Okay, this is V naught, and okay, so this is the one. Okay, so this is V naught, and I have defined this potential, right? And uh, the wave is coming like this. sinusoidal wave. Okay, that is this is the oscillation wave is oscillation wave. Okay, and from here this is E. Okay, E, and here we can see in this case E is less than V naught, right? So here the penetration is possible, and this is going to be like this. Okay, like this. Yeah. So this is the case one. Case one. This is called region first. Okay, and this is region second. Region second. Okay. This is region second. Okay, and this is the case number one where E is less than equal to, this is the energy and wave is coming, right? And V naught, this potential is greater than energy. Okay, that is V naught. And now we'll find Schrodinger equation for region one. Okay, for region one. Schrodinger equation is going to be d square psi 1 upon dx square plus 2m upon h cut square E minus V equal to 0. This is Schrodinger time independent Schrodinger equation. Okay, time independent Schrodinger equation. Okay, so now in this case V, the V is defined, right? V is here for region first. You can see V is 0 because for x equal to less than 0, the value of V is 0. The potential is defined like this. Okay, so in that case V is going to be 0. So this Schrodinger equation is going to be d square psi 1 upon dx square plus 2m upon h cut square E equal to 0. Okay. Now we can write this like this: d square, there is psi 1. Okay, this is psi 1. Okay, so now we can write d psi 1 upon dx square plus k square psi 1 equal to 0, where value of k is root 2me upon h cut square. Okay, this is, and now we can solve it. Auxiliary equation for it is going to be auxiliary equation is going to be m square plus k square equal to 0. So it means m equal to plus minus iota k. So therefore the solution is going to be psi 1, which is going to be e to the power a e to the power iota kx plus b e to the power minus iota kx. Okay, yeah, this is because k is this, the value of k is this. Okay, now for region 2, so if you see region 2, and here also I would like to explain, if m equal to this I can also explain. Okay, very important point. If m square plus k square equal to 0, it means m equal to plus minus iota k, right? So if that is the case, then the motion is oscillation motion. Okay, oscillation motion. Wave motion is oscillation motion. Okay, and if m square minus k square equal to 0 implies m equal to plus minus k. M equal to plus minus k. In that case, this is non-oscillation motion. Okay, non-oscillation motion. Very important point. Okay, if m equal to plus minus iota k, imaginary number, then it is oscillation motion. If it is real number, value of m is, then it is non-oscillation motion. Okay, so for region 2, you can see this Schrodinger equation, time independent Schrodinger equation is going to be, which is d squared psi 2, this region, upon d x square plus 2m upon h cut square e minus v psi 2 is going to be equal to 0, right? So now, okay, the value of v is, this is going to be v naught, right? Because here we can see there's a condition, right? This one, if x is greater than equal to 0, then the value of v is v naught. Okay, so this is the key, because we are talking about region 2, this region here, it is x greater equal to 0 region. Okay, so this is going to be e minus v naught, or we can write it d square psi 2 upon dx square plus 2m upon h cut square. Meanwhile, let me check the connection. It is fine actually. Yeah. Okay, so this is going to be, we can write like this, because v naught is greater than e, right? So we can write like minus, we can write e naught minus e psi 2 equal to 0. Okay, so this is going to be like del square psi 2 upon del x square minus k square, or we can write alpha square psi 2 is going to be 0, where value of alpha is root 2m upon h cut square v naught minus e. Okay, 2m upon h cut square v naught minus e. Okay, this is one. Now we'll solve this equation. So this is going to be the auxiliary equation is going to be m square minus alpha square equal to 0, because this is alpha. Okay, value of alpha is this. So this is going to be m equal to plus minus alpha. So equation is, so Schrodinger equation, that wave function is going to be c e to the power alpha x plus d e to the power minus alpha x. Okay, Well, now at x equal to infinity, psi should be 0, right? Must be 0 at x equal to infinity. So this means psi 2 should be 0, right? So we'll write at x equal to infinity. So it is going to be c e to the power infinity plus d e to the power minus infinity equal to 0. This term is going to be 0. So in that term, c e to the power infinity equal to 0. Infinity e to the power infinity cannot be 0. This implies c equal to 0. And this implies the wave function psi 2 is going to be, because c is 0, so d e to the power minus alpha x. Okay, d e to the power minus alpha x. This is the wave function. Okay, next. So now I'll explain. So these are the function of psi and this, right? Now psi incident, okay, psi incident is going to be is in this term e to the power iota kx. Okay, this is real wave function, guys. Okay, there is no answer. This means oscillatory motion. There is no non-oscillatory motion. Okay, there is no oscillatory motion in this wave. Okay, so this is e to the power I kx. Okay, so this means direction is so in incident wave in positive x direction. Okay, so this one. This term, okay, incident wave in positive x direction. So here we can see this is like this direction. Okay, similarly value of psi reflection is going to be b e to the power minus iota kx. Okay, this one, this wave will go from here. If this is a barrier, then this will get reflected, and that is b e to the power minus iota kx. Okay, and this is a potential barrier. We can see an energy is greater than E, right? Energy is less than V naught. V naught is greater than E. So in that case, because it's a quantum mechanics, right? Quantum mechanically, so there is a probability that the wave will also will penetrate this barrier and will go in second region, right? And because we have seen this is a real function, so the wave will be like this. There wouldn't be any oscillation motion. Okay, so well, similarly, that is called which will go in and second region, that wave is called transmitted wave. Okay, transmitted wave function is going to be d e to the power minus alpha x. Okay, so this is transmitted wave in region second. Okay, this is incident wave in plus x direction, okay, and this is reflected wave in minus x direction, and this transmitted wave in region 2. Okay, region 2, I will show you in figure, this one. Okay, this is transmitted wave, this is reflected, this in this direction incident wave. Okay, well. So these are the wave function and by Schrodinger equation we have found. Now we know reflection coefficient. Definition of reflection coefficient, that is R. R is called reflection coefficient. Reflection coefficient. Reflection coefficient, and that is mod B square upon mod A square. Okay, this is the reflection coefficient. And there is a formula we know, R plus T, that is reflection coefficient plus transmission, sum of reflection coefficient plus transmission coefficient is equal to 1. Okay, and where T is transmission coefficient. Transmission coefficient. Okay, transmission coefficient. Transmission coefficient. Okay, well, this is one. Now we will use boundary condition. Okay, boundary condition for this equation. This is for this is the case of when E is less equal to E is less equal to V naught. Okay, so now boundary condition, we'll use boundary condition. Boundary condition. Boundary condition, right? We know that is psi 1 at x equal to 0 is going to be psi 2 at x equal to 0. Okay, similarly del psi 1 at x, del psi 1 upon del x at x equal to 0 is going to be equal to del psi 2 upon del x at x equal to 0. Similarly, yeah, so these are the boundary condition we'll use here. Okay, so first the psi 1 equal to, this is a e to the power iota kx plus b e to the power minus iota kx. Okay, at x equal to 0, this is value of psi 1. Okay, I'll show you the psi 1, this one. Okay, and the psi 2 is this is psi 2. Okay, so similarly here psi at x equal to 0, right? So this is going to be d e to the power minus alpha x at x equal to 0. First boundary condition, this is first boundary condition, this is second boundary condition. Okay, so we will solve it. So we will put x equal to 0, so it is going to be a plus b, because e to the power 0, e to the power ik into 0, e to the power 0, e to the power 0 is going to give value 1. This is equation number 3. Okay, now we'll differentiate it and we'll put it differentiate and at x equal to 0. Okay, so this is going to be, after differentiation, this is going to be ik a e to the power iota kx minus ikx e to the power minus iota kx equal to, we are differentiating. Okay, so this is going to be minus alpha d e to the power minus alpha x at x equal to 0, at x equal to 0. We'll solve it. So this is going to be ika e to the power 0 is 0, 1, right? Ika minus ikb, there is b as well, ikb. Okay, ikb equal to minus alpha d. Okay, e to the power 0 equal to 1, right? Next, so this is going to be, now from here we'll find the value of D. So D is going to be, value of D is going to be this one, ik. So we will take common, right? So this is going to be minus ik a minus b upon alpha, right? Because this minus will go here. So this is going to be this. Okay, so now what we are going to do is here, so now this is equation number 3 and this is equation number 4. Okay, now from 3 and 4, from 3 and 4, what we'll do, we'll use 3 and 4, and 3 and 4 will put value of D into this. So this is going to be A plus B equal to D, right? So this is D. So D means we'll put the value. D is going to be iota k A minus B upon alpha. Okay, and we'll solve it, and from there we will get, and also here we know the value, right? We know a value of alpha and k as well. So this is, if we solve it, it is going to give B upon A. The value of B upon A is going to be minus, no, it's not minus. So this is going to be 1 minus iota k upon alpha upon 1 plus iota k upon alpha. Very important formula, guys. So there's a question which is asked in the CSIR net question using this formula. Okay, so I will solve it also maybe in next lecture, because this lecture is going to be lengthy lecture, B upon A. Okay, so because I will solve, I will complete, I will discuss complete step potential. Okay, all two cases. Okay, so this is the one. Okay, very important formula. So this is 1 minus iota k upon alpha upon 1 plus iota k upon alpha, where a value of k, you know, 2me upon h cut square, and alpha value is 2m upon h cut square v naught minus e root, right? And from there also the value is going to be alpha upon k is going to be root v naught upon e minus 1. Okay, so in place of alpha upon k, you can write this iota root v naught upon e. Okay, v naught upon e minus 1 upon 1 plus iota root v naught upon e minus 1. Okay, so this we can also write. This is an important one. Okay, well, so this is about b upon a, value of b upon a. Okay, so now next, before that, next we are going to study, before proceeding further, there are some points which I'm going to discuss. This is probability current density. Okay, I'm going to discuss probability current density. What is probability current density? Okay. Okay, so probability current density. So first I will write equation of continuity for charge. Okay, flow of charge. So that is divergence J plus del rho upon del T is going to be 0, right? So this is the equation of continuity for flow of charges. Okay, flow of charges, flow of charges. Okay, so here divergence J is denoting, saying diverging current density. Okay, so current density is diverging. Okay, diverging current density. Okay, and minus del rho, this is rho. Okay, del rho upon del T is going to is decreasing charge density. Okay, decreasing charge density. How? Because this equation we have written